All right, let's get started. So, hello once again, guys. Hopefully you're fine. Hopefully you're all well. To start off the class, going to start with some announcements. And the first one is hot off the presses. So I got the email like a couple minutes before the last class that I taught. So I told them about it, and now I'm going to tell you. My first class, I got it after them. So I'll like alert them in an email or anything, something like that. So the math department has finally spoken about the final, and basically the answer is, as I suspected it would be, is they're pretty much leaving it up to the instructor. So they have a few guidelines on what they want the final to be like, but other than that, you really have your freedom. So I've decided that the protocol that we're going to use for the test, we're going to just do the same thing for the final. I have a feeling that it's going to work well, so I think we'll stick to using it. So that is what your final will look like. Also, that being said, to tell you a little bit more about what the test would be like. So the test is going to be online through a platform called Top Hat. They've been around for years, so they are an education platform, but they never really went into the proctoring sphere. So they're just starting to do that now, and I think this whole situation kind of really sped up the process of them jumping into that field. But yeah, we're going to use them. I was on Zoom calls with them up to yesterday. We worked out a lot of the technical issues, and I even uploaded some practice tests on their platform, and I think it looks pretty nice. I think it's going to work very well. So that's what we're going to do. In that regard, you should look out for an email over this weekend. Might come tonight, might come tomorrow, latest by Sunday. So I'll send out emails through the platform that will invite you to the platform to register for an account. It will operate through your browser, so you're not going to have to download anything, but you're going to use a Chrome extension in the Chrome web browser. So you have a laptop with a webcam that can use Chrome. You can take the exam using this protocol. That's what we are doing. And yeah, instructions for that will be sent out later today. And what I want to do in the ideal world, as I mentioned to all my other classes, I'm giving everyone exams next week and practice exams. But what I'd also like to do is to post another practice exam for you guys, maybe a practice quiz. I don't know. I'm going to see what I have time to get out this weekend. But I'll probably post another practice exam that you guys can take early next week on the platform, just to see what it would feel like, just so that you're prepared, you'll know how it works. And yeah, you'll just get some getting used to it. But basically, just to describe in a nutshell what that's going to be like, is you're going to open the browser, you're going to log into the platform. The questions are going to be in the platform. So you're going to go through the questions, click, okay, question 1. You're going to write it out on paper. You're going to do question 1, and then you're going to indicate that, okay, I did question 1. Boop, move on to question 2. Read question 2. Do your work. Okay, did question 2. Okay, read question 3. Okay, did question 3. And you're going to go through it like this. And then at the end of the day, you're going to submit. But of course, you're not going to have any answers on the platform itself, because of obviously typing out answers in a class like this is going to be really annoying. So what you're going to do is you're actually going to, the paper you're writing on, hopefully you wrote very neatly, you're going to scan that and send it in. And it also has an app where you can scan from your phone that's connected to the platform. But if you have a regular scanner, you can scan it on to your computer and then upload it through the browser as well. So that's basically it. It is going to be like a written exam. You have to show all your work. I'm going to grade you for partial credit, the whole shebang. The only difference is you now have this online component that you have to check into and that you have to upload your work to. And so that's basically how that's going to be. It's going to be through the Top Hat platform. Like I said, instructions are going to be sent out about how to access that platform this weekend. And the final, I think, will be done the same way. And yeah, so that is how the exams are going to go. Another announcement I wanted to make before I forget is that it was in the same email that the math department sent out today. So I want to make sure I mention it in case you weren't aware. Today is the last day, as far as I know, according to that email. I didn't verify this from the other source, but according to that email, today is the last day to apply for a pass-fail grade. So if any of you want to do that, now's the time to get it done. That being said, whatever your grade is now, I do not anticipate anyone getting a worse grade than they currently have. So if you're in a situation where you're not sure if you should apply for a pass-fail and you look at your current grade and you're like, I'd be okay with that. Like, you really have to mess up really bad to not get at least that at this point, I feel like. I don't think anyone's going to get lower than that. The potential is that you would get higher than that because, for example, the final is cumulative, so it will cover test 1 material as well. So if you didn't do so hot on test 1, but you did well on the test 1 material on the final, your test 1 grade is going to matter even less to me. I'm going to be like, okay, now they got it. So that could boost your grade even more. Whereas if it's like you show that you didn't really learn, if you do at least as well as you did on test 1, which I think everyone should be able to pull off, your grade is roughly going to be the same. I think the material after test 1, based on the limited feedback I've been getting from you guys actually feel a little bit more comfortable with that material. You guys actually feel better. So that being said, I think there's a good chance that no one would end up with a worse grade than they currently have. And so if you are considering that option, you should probably take that into account. And I see Syed raising his hand. Do you have a question?
Yeah, sorry, I have a question, but if you were saying something, you can continue. I just had a question on the application that we were using. What is it? Hat something?
It's called Top Hat, TOP space HAT. And the website is Top Hat, one word, TOPHAT.com.
Sorry, so the question I had was, you said that we have to go on the website and then we have to do the question, and then we have to click on the question and do it handwritten or whatever.
Yes.
So we have to do the exam in order. We can't do the exam out of order. And can we go back to, I'm a bit confused. Like, can we go back to a question?
Yeah, you'll be able to toggle between questions. I don't see why. In terms of in order, I think the questions will be randomized. So there's no real order. So if you see a question that you don't really know what to do, you just move on to the next question and just make sure that you come back. And that's why you're going to indicate that you've actually completed the question. It's also going to remind you that, hey, you didn't finish everything. When you get to the end and you realize, oh, I didn't check in that question, it should go back. So
the other concern I had, real quick, sorry,
yes.
were you saying something?
No, go. That was my
other concern I had was, I know from I just took a physics exam or whatever.
Mm-hmm.
My other teachers, whatever, they allow me a little bit, like 10 minutes or something, since I have a printer and I need to scan it. So I just want to.
Yes. So I will give you guys extra time. It'll be. So strictly speaking, an exam is going to be 50 minutes long. I will put the timer for something like 60 minutes instead. So there's a 10-minute buffer in case you have any technical issues or your internet starts acting up. You can probably do that. And I'll probably add an additional 5 minutes on top of that for you needing the time to scan in and send in your work. So yeah, I will put a little buffer at the end for you to get time to upload that stuff. So yes, that will be considered. That being said, I also sent out an email. If any of you have signed up with the Student Disabilities Office and you're entitled to extra time, you need to let me know, because I'll have to manually change the time. So those of you who have signed up know who you are. And if any of you happen to be in this class, you need to let me know. All right, Joseph.
This is a completely unrelated question to what you guys are talking about, but
okay.
I went on to WebAssign last night just to see if there was I don't know, any homework or
yes,
just to go check, and it said that I clicked on the it's it says where it says purchase course, and then it says all the information about it. I clicked view on that. It says I'm no longer enrolled in it, and I can't access any of my past assignments or my gradebook. And
yeah, that's strange. We'll deal with that outside of class. That sounds like something that I need to actually go in and check on. Okay. But yeah, shoot me an email, remind me of that issue. And if any of you are having similar issues with the online homework, let me know. and I'll definitely get on that.
Yeah, thank you.
Okay. Any other questions? So our test Wednesday next week. I will probably, in an ideal world, have a practice test to run for you guys, and maybe I'll actually do that in recitation, so you guys can actually feel out the platform during recitation. I'll maybe either put your quiz on that platform or maybe an additional mock test on that platform. So afterwards, you can discuss that with Rolf. And you'll be sent an email this weekend about how to sign up for that. And yeah, the final is going to have the same format. Today's the last day for pass-fail. That's it. I think that's it. One other thing I wanted to mention is I think I've been counting up the lectures, and I think we're a couple lectures short. So there are some, I will want to upload maybe like 2 lectures, probably asynchronously. And I'll just try to make those lectures things where it will be kind of boring for you to sit through it anyway. So like definitions and just me telling you about stuff. So that we'll look out for that. And yeah, so my idea is I kind of want to end the semester with talking about cross products. We're ending around there. So I want to finish talking about 3D here. Oh yes, the test is Tuesday. So I'll upload a practice test that you can try out on Monday or something like that. That was from a comment. Okay, so that's kind of where we are. I think with that we can start to jump into the lectures. So let me share this. And that's not where we are. We're in this section over here. So I want to get up to like here, like cross products, and I'll be actually happy with that. This is something that we started last class, talking about the 3-dimensional space. We are going to continue that discussion. Oh, also something else. So, some people were asking, they weren't sure, is the timing of the final exam specifically, has that changed? As far as I know, it has not. So currently when I go on the final exam website for the college and I click on the final exam schedule, you will notice that the schedule is still the same one as the one I posted in the syllabus. So our class is Tuesday, Wednesday, Friday, 1:30 to 2:20. So your final exam is Wednesday, May 6th at 1:30. This is, you are seeing me check this final exam schedule in real time. So as of today, the final exam schedule has not changed. So I don't think it's going to change in the next week. So yeah, so your final exam is on May 6th. We'll be using the same protocol that we are using for the test remaining. Okay. So I just wanted to also cover that, make sure you know that it's going to be the same time. All right. So that being said, let's actually jump into things here. So we'll do a few calculations here, but most of today, again, is still just kind of getting used to this new environment. So a lot of it is just going to be me talking about certain concepts that you want to keep in mind when talking about 3-dimensional space. But eventually we'll talk about some stuff to do in the end, which we should get to in a few minutes. That being said, just to minimize the risk of glitchiness, I am once again going to turn off my video and you can just listen to me move around here. So, all right, moving on. So last time we introduced the 3-dimensional space, the rectangular coordinate system. Here's how we graph those. X-axis goes off here, Y-axis goes off there, Z-axis points up. And in your whole life, you had a bird's eye view looking down at the XY plane. And this is the picture you were seeing, but there was like a Z-axis pointing straight up out through your forehead. This guy, that's the 3rd dimension. And of course, perceptually speaking, as far as you can tell with your eyes and how you experience reality, we live in 3 dimensions. So knowing how to do math in 3 dimensions is going to be an important thing. And this is something that you're going to get into in multi-1 and multi-2. But I just wanted to give you guys a head start on the environment that you will be doing calculus in, and some important objects that you will need for that study. The three-dimensional coordinate system is such a thing, and it's the first coordinate system you will learn about is the rectangular coordinate system, which works similar to how it does in 2D, except now there's a third straight line that you would add to this to rise to the level of Z. And then at the corner of this box, the corner of the box totally opposite to the origin is the location of your coordinate. We also saw last time what we name certain planes in this space. So if you're someone standing in a room facing a corner, you can just imagine that you are on the second floor of a two-story building and you are standing in the first octant. The wall to your right, if you're facing the corner, the wall to your right is going to be the YZ plane. It has equation x equals 0 because all coordinates of x along that plane will be 0. The wall to your left will be the XZ plane, and the floor you're standing on is the XY plane, which was your universe up until this point, as far as math class is concerned anyway. And these planes split space into 8 octants, quote unquote. So back in single variable calculus, we had 1, 2, 3, 4 quadrants. So they were called quadrants because there were 4 of them: first, second, third, fourth. Now we have 8, so we call them octants for octo 8. So the first octant is where all the coordinates are positive. Second octant is behind the right wall. The room opposite that is behind the right wall of that room is going to be the third. Then the fourth is behind the left wall. Below the room below you is the fifth octant, then the sixth, then the seventh around here, then the eighth, right? So that's how we are going to envision 3D space from now on. There are 8 octants. Now, that being said, most of your work is going to be done in the first octant. It's the only one that you're really expected to know where it's located. Most of the time, I don't even see people mentioning how the other ones are numbered. The first octant is what you really need to know about, because literally the phrase "the first octant" will show up in problems for you to do. Oh, this is going on in the first octant. Do blah, 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 right? And you should know that, oh, I'm in this location here. All right. So now we want to talk, so that's the space in which we're working in. Now we're going to want to talk about objects in space. And this, basically the objects that we are going to care about are vectors, which we'll talk about in the next one, surfaces and solids, and of course curves, right? So we want to talk about how these guys will behave in space. As far as solids are concerned, we're not going to even touch on those in this class. But we will see surfaces at this point and be able to stitch them together. And so I want to just bring to your attention certain things. So we're in 3D space. I want you to think about these objects here. This equation, x equals 1, y equals -2, z equals 3. Does anyone want to guess what kind of object this would be? So if we were back in single variable calculus in the xy plane, that was our entire universe, x equals 1 is just a straight line. It's a vertical line passing through where the x coordinate is 1. What do you think it's going to be in 3 space? What do you think x equals 1 would actually look like in 3 space?
A plane.
It would be a plane. So give myself some more space here. It would actually be a plane. So let's actually look at what that would look like. So we would draw our axes in the way I mentioned before. So this is x, this is your y, this is your z, and we know that this goes back like that, this goes back like that, this goes back. So those are the negative versions of the axes. And here, just pick a point, that's x equals 1. Now, in 2 space, there's just a vertical line putting through this, but you'll notice if you rise directly above that point vertically, you're still in a situation where the x coordinate is 1. And so all of those such coordinates will work. So there is like a literal plane slicing through here, and it extends forever in all directions. But this is what x equals 1 would look like. And it will literally keep going in all directions. but we can just draw a rectangle to represent it here. And so this is a rectangle that's standing vertically up in space. So if you were in this room, this could be like a wall partitioning the room. It'll be a vertical thing. It'll be a flat sheet. Theoretically, it has no width. Of course, you know that in reality, that can't be the case. But yeah, there's a flat two-dimensional sheet with zero curvature, as we would call it. We know such an object to be called, it's a plane. Similarly, if you look at y equals -2, here you'd find -2 over here. Say that's y equals -2. And yeah, all points along that would be just a horizontal line if you're looking at the bird's eye view, but then there's just a plane passing through that. And that's your plane, y equals -2. And of course, you can move over to the Z one, for example. Z equals 3. This would also be a plane. So if you draw the axes, find the point where Z equals 3, and you will just have a flat sheet. It'll be hovering over the XY plane. It'll be actually parallel to the XY plane. And again, these extend in all directions, but it stays flat. The distance above the XY plane is always going to be 3. So if you're in this room, just imagine like the roof is 3 meters above you, and you're literally looking at the roof, a 3-meter high roof. It's a horizontal thing just moving above you. And so that's what these objects would look like. These guys are planes. And this is something that you're going to explore a lot more in Multi 1, actually. So you're going to look at planes in general, but you should know that things that looked like lines back in Calc 1, or even the earlier part of this class, they are actually planes in 3 space. Right? What about y equals x? Well, again, that's a similar thing. So you know here in R2, which is 2 space, y equals x was just a line that passed through the origin, going like that. But of course, in 3 space, in R3, as it's sometimes referred to, that's the line that would be tracing out here. And again, that would look like a plane moving back. But it will slice through the XY plane along the line. This is the line y equals x in R2. Okay, so these equations here are planes. They look like lines to us, but that's because we're living in a shadow of what reality actually is. And the matrix wants us to think these guys are lines, but in reality, they are planes. You go to a higher dimension, you realize, oh, that y equals x is actually a plane. It just looked like a line because I had the bird's eye view. Now we are seeing more of the truth, more of what reality is. So in 3 dimensions, these equations here, y equals x, looks like a line to you, but you should know it's actually not a line. In 3 space, it's a plane. Let's look at some other objects. What would this guy look like? So this is you would recognize this guy as a circle. And spoiler alert, in 3 space, it is not a circle. What do you think this guy would look like?
A cylinder?
A cylinder. So you can draw, again, the axes. X, Z, Y. And so in R2, you would see this picture, a circle of radius 1. Okay, that's what you would see in R2. So essentially, that is what you're seeing here down on the floor, right? There's just a circle of radius 2. However, if you were to go up a notch, right, and your Z value was something else, you would also see a circle of radius 2. All those coordinates on here will also have x squared plus y squared equals 1. And if you go down, you would also see a circle of radius 2, right? Notice here that the z coordinate is not mentioned, which means this is the relationship between x and y, no matter what level of z you are at. So pretty much at any level, how you move up and down the z-axis, you're always seeing this. The results of that is something that's called a circular cylinder. So there's actually a cylinder here. Right? And again, it extends forever in all direction. It is hollow inside. It's empty inside, just like my life. Okay, it's hollow inside, but it would look like a cylinder. It will run up and down. It'll actually be this equation for all z values. So again, in 2 dimensions, that guy's a circle. In 3 dimensions, no, it's not. It's actually, that circle that you were seeing was literally just where it intersected the xy plane. But there's more to the story here. It's actually a cylinder, right? Which is a generalized version of a plane. You take a plane and you kind of wrap it in a circle and you get a cylinder. Okay, now let's talk about distances in 3 space. Knowing about distances, how far one thing is away from the other thing, is going to be very important. And it turns out that Pythagoras' theorem also works in 3 space. So it turns out that if you have a distance between 2 points, if you have 2 points here and you care about finding that distance, okay, this is point 1 and point 2, what you can do is in the xy plane, there are 2 points. You can use a distance formula in the xy plane to figure out the distance here. So that's the first 2 parts of the formula here. And that will help you find this length of this triangle that we could have up here. But you'll notice that I can form another right triangle. So I can find this length using Pythagoras' theorem, because that's how we did it back in 2D. That's where the distance formula came from. And then that just helps us find one length. And then to find this length here, apply Pythagoras' theorem to this and that. And that's just you extending this formula. So the distance formula still works out. That being said, if we want to talk about an object that is the same distance from some central point, so here's this point, and I want all points that are a distance r from that point. Pretty much all I do is I go to this, I plug in r here, and I can square both sides, and I get this equation right here. This is the equation of a sphere. So a sphere is just an object that consists of all points that are equidistant from some known point. This is a 2-dimensional object. Again, once it's equal, it actually means the sphere is just the outside. It is actually, again, hollow inside. Right. If you wanted to fill in everything, you could put a less than or equal to sign here, and that would be called, what else? A ball, right? So, so this is an object of the sphere. We can figure out its equation just by applying the distance formula. So something very analogous to the distance formula in 2 dimensions does work in 3 dimensions. And in fact, it works in all dimensions. So even if I was in 4th dimension, there'll just be another sum of difference of squares here. There'll be another square of a difference being added, and you just add that. And so yeah, this actually works out in general. This is something, whenever a formula is like that, where by adding a dimension or the formula just extends very naturally, we say it generalizes naturally. You'll see that phrase all the time. So when someone says, oh, it generalizes naturally, it just kind of means that, oh, it'll extend the formula in pretty much exactly the way you would guess that it would extend it. When something is not natural, it means it's something you have to prove and convince someone of. But this is like most people would actually guess that's how you'd find the distance in 3D. Example, show that this thing, here's a random equation with 3 variables. Show that it's the equation of a sphere. What is its center and radius? All right, maybe tell me how would you go about showing that that's a sphere and determining its center and radius? This is where you guys come in, ideas.
You move everything to the other side and then complete the square.
Right, so completing the square would be the trick. Okay, so let's actually do that. So we have x squared plus y squared. So move everyone over, x squared. And you would tend to want to group like variables together. So you put the x's together, put the y's together. And then you'd have just your z squared all by its lonesome, and you have 0 over here. Now you're going to complete the square. Remember how we complete the square? We are going to add now, let's not worry about that. This is good enough. Okay, so you are going to add a square to both sides. The square that you add should be a half the coefficient of the linear term squared. So over here, you're going to add a -2 and square it. You have to add that to both sides to maintain the equation. And for the y, half of +2 is a 1. So you're going to add a +1 and square it. Add that to both sides. Now, these guys here become a complete square. It is going to be x plus the guy inside here, all squared, plus y plus the guy inside here, all squared. And over here, we are going to have 5. So that should automatically look like this equation to you. And so now you can talk about the center and the radius. And what are these? What is the center and radius here?
The center would be 2, -1, and 0, while the radius is square root of 5.
All right, I'm still stuck in 2D here. Let's not forget it's 0. And that's because there's like an invisible z -0 squared here. Okay, and that's it. So this is a sphere. And that's that. So you would look at this equation, x equals 1. In 3 space, you know that's a plane. And you would look at this equation, x squared plus y squared equals 1. And in 3 space, you should know that that's a cylinder, a circular cylinder, in fact, where when we slice it, we just see circles of radius 1, if we slice it parallel to the xy plane. Then if you see an equation like this, then if you see an equation like this one down here, you'll know, oh, that's actually a sphere. And you're going to learn about a lot of other equations that are kind of like this, but the signs here might be different. These guys are called quadric surfaces in general, and you'll actually learn how to sketch those in, do I have an example of those? I mean, we're not going to worry about it really, but well, we're not going to worry about it. So you'll see more general things here, but this is actually a sphere. And of course, you could sketch that if you needed to. Another important concept is the idea of regions in 3 space. So sometimes you're going to be needing to solve problems in such a way that you're not going to just know about some individual equation that you're looking at, but you are going to want to know how equations relate to each other. So you're going to see some random equation in 3 space, some function of x, y, and z, and then you're going to know, oh, this one over here is a sphere, that one is a cylinder, and that one is a plane, but they're all interacting in this way. And you're going to need to know positionally, you're going to have positional awareness and spatial awareness of how these guys relate to each other. Like, oh, that's a sphere, and that is the roof of this region. And then, oh, there's a cylinder here, those are the walls of this region, and this plane would be the floor. So this one is above that one, and this one is beside that one to the right. And all this kind of awareness you'll actually need in the next course. So to talk about that, let's actually talk about how you would actually go about getting this awareness. So regions, I just want to remind you, we're in R2 here. So just to remind you how you'd think of regions, they're not just curves, right? So if we're in our XY plane, like in the good old days of last week, and you want to sketch a region like y is less than or equal to x, what would that region look like? How do you go about doing that?
Basically, you graph y equals x, and then everything underneath it is shaded.
Right, so here is y equals x. You'll notice that above that is where your y's are greater than or equal to x. And you can tell by picking any one coordinate, like 0, 1, you realize, oh, the y coordinate is bigger than the x coordinate. But then you'll notice over here, say like 1, 0, the x coordinate is larger, and that's the one you want. You want the x to be greater than or equal to y. So you actually want this region down here. So it's not just a curve, it's an entire region of space where the curve is kind of just telling you about the boundary. Of course, you could have y strictly less than x, and that will be a very similar idea, except you would draw a broken curve. And that indicates that on the line is not a part of the solution, it's not a part of the space that you want to consider, but it is still somewhat indicating a boundary. And so that would be this. And this does not include the line. Okay, and this one over here includes the line. Since it's a less than or equal to. And here, it's just less than. So it doesn't include the line. So that's the region in 2 space. Yes, we're all familiar with that. In 3 space, things get a little bit more challenging. So let's actually jump into 3 space. Example, what is the region bounded by this inequality in the first octant? So there, that phrase shows up, first octant, okay? If you were to sketch a picture of that, what region is it talking about? Okay, so now we're in 3 space because I know there's a z coordinate here. What are we actually looking at here? This goes back, this goes back, this goes down. Ideas on what that would look like? A circle that is centered at the origin? What do you mean a circle?
A sphere.
It's a sphere. So you see here, you see x squared plus y squared plus z squared is less than or equal to 1. That should remind you of this equation up here. X minus a squared plus y minus k squared plus z minus l squared equals r squared. Here, if you plug in h equals 0, k equals 0, l equals 0, and you plug in r equals 1, you will obtain the equation here. Now this says we're less than or equal to 1, so what does that mean?
The radius is 1.
right? What does the less than or equal to 1 mean?
It means it's not hollow.
It's not hollow. So you're filling in everything inside the sphere. So you want all distances that are going from 0 all the way out to 1. What does the first octant mean?
All the coordinates are positive.
Okay, so describe what that would look like in this thing. So normally when you have a description like this, what I would recommend you do is that you should draw the entire surface you should draw the entire surface. So we know this is a sphere. What I would do is I would draw a whole sphere to start off, right? But this is very faint. It's not a part of the picture. So you can draw a sphere by just drawing a circle, what looks like a circle, and then you draw that could have been better, but I don't want to do that over. Then you draw an equator, right? And that kind of looks like a sphere. And now you go and you look for what you want, less than or equal to 1, and in the first octant. So in the first octant means I want the XZ plane, the YZ plane, and the XY plane to slice the sphere off. So the wall here is going to slice out a part of that sphere. Also, the wall over here is going to slice out a part of that sphere. And then, of course, the floor is going to slice out a part of that sphere. And so that should look a little bit more symmetric, but I think you guys understand what I mean. So this is the object that we care about here. Boom. 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 And it actually goes so that's our guy, that's our sphere. So we want this. Okay. And this is solid now, it's filled in. Solid, right? So that's just a part of that sphere. The part that's stuck in the first octant, which means it's like if you had a ball, it's 1/8 of the ball. Like if you were to slice that in half and then slice the half into quarters, this is one of those quarters. Okay, so that is that region. Follow-up, bonus. How can you describe this using different inequalities, particularly inequalities in polar coordinates? So let's see what we remember from polar coordinates. So remember, polar coordinates means that the x and the, so instead of telling me about x, y, z, you want to tell me about r, theta, and z. By the way, in 3D, this is referred to as cylindrical coordinates. And when you get to multi-1, you'll realize why they called it that. So in this universe, we would describe this guy as x squared plus y squared plus z squared less than or equal to 1, where my x is greater than or equal to 0, my y is greater than or equal to 0, and my z is also greater than or equal to 0. So if I set up this description here, that set of inequalities will actually describe this object. I would like you to tell me what a description would look like in this universe here. in the cylindrical universe?
R is less than 1, but greater than 0. Or less than or equal to 1, and then greater than
Yeah.
0.
Theta?
Theta is from 0 to pi over 2.
Yep. Because
And-
that theta is in this plane right here. That's where your theta is. And I don't know if that's exactly clear. That's where your theta is. And that's, it goes through a 90-degree angle. And then what about Z?
Is z from 0 to 1 as well?
No, because Z equals 1 is like it's like a flat plane,
Oh,
right? So your roof here, the roof is the sphere. Now, of course, your Z here is positive, so you actually know what that is. This is just Z is equal to the positive square root of 1 minus x squared minus y squared. But of course, so that's how you would describe the what Z goes up to. So it definitely starts at 0 and it goes up to that. So it starts at 0 and it goes up to what I just described. However, there are no X's and Y's anymore. So need more space here. So how can I describe that? How can I turn this into something that doesn't use the X and Y, but rather uses the R and the theta? Ideas?
would it be something about the surface area of the sphere?
No.
Okay.
I'll give you a hint though.
Can't you use x equals r cosine theta and then y equals r sine theta?
You
And then
could,
plug the r's
but
and the theta.
this expression is also something that you know. X squared plus y squared, that's equal to what in polar? What is x squared plus y squared equal to? Polar coordinates. That's actually r squared. So your z would actually go radical of 1 minus r squared. And yes, if you plug in r cosine theta for x and r sine theta for y, you'd get a common factor of r squared. You'd factor that out. You'd left over the factor of sine squared plus cosine squared, which gives you 1. So you can get r squared by plugging those in. But x squared plus y squared equals r squared is really something that you just want to have automatic. Every time you see that expression, you just know whenever you're thinking polar coordinates, x squared plus y squared is r squared. You don't want to take too much time to get to that. So that was just a bonus there. And we're pretty much out of time. Let's just get through this last one quickly. And that's the last example I want to wrap up in this section. So here's the description. And let's actually see how this would actually work out. So again, I'm going to draw my axes here. And I know that there's a negative x-axis going off there. There's a negative y-axis going off there. And what's this chat box on? And there's a negative z-axis going down here. Okay. And so now I'm going to look at this description. Notice what it says is two things. I know that 1 is less than or equal to x squared plus y squared plus z squared. I also know that x squared plus y squared plus z squared is greater than or equal to, is less than or equal to 4. These are both describing spheres from earlier. So I'm going to go in and I'm going to draw those spheres. So there is a sphere of radius 1 in play, which I can sketch like that. There is also a sphere of radius 2 in play, which I can sketch like so. All right, now I know that I want to be greater than the sphere of radius 1. So I want to be outside of the sphere of radius 1, but I want to be inside the sphere of radius 2. So I know the in between here is a part of the region that I care about. So now I also see, well, what is the region that I care about? I want y to be less than 0. and I want my z to be greater than 0. So I want to be behind the x-axis. I want to be over here, behind the x-axis. And I also know I want to be above the xy plane because my z is greater than or equal to 0. So now you can just start tracing out the parts that you actually care about. So that means I want to be behind this. So that's that line. That's that line. And then also for the bigger sphere, that's that line. It's that line. So this wall here is the beginning. Now, of course, inside here is going to be hollow. And then I want the part that's behind the XZ plane. So it's going to be the back here. Okay. So you have that guy, kind of like an eighth of an avocado or something. You remove the seed and you slice it up. And so that is our object. Okay. Now in the next class, being able to put together a bunch of surfaces like this to create some sort of object, that's going to be very, very important, right? So if you live in 3 dimensions, you want to do math in 3 dimensions, you are going to want to know how to talk about objects in 3 dimensions. And so oftentimes what we do is we put together the surfaces of the object, we kind of stitch them together in a way like this, and we can describe this using a series of inequalities, right? So that's the object that we now have, right? And that would describe a region in space that we might want to do things with. So just like how we can draw a curve in the XY plane and we can talk about the area under that curve, we might have a surface in 3D and we want to talk about the volume of that surface. And we want to might do things on that surface, like integrate on that surface, differentiate on that surface, do all sorts of things with that object. But knowing how to conceptualize the object is, of course, going to be the first step. And so that's just putting some of these ideas together. But the general principle still holds. Draw the objects in their entirety, and then start slicing away what you don't want, and just kind of highlight what you do want. And that's how we can describe regions in 3 space. So as I mentioned earlier, we'll wrap up there, but as I mentioned, probably the next lecture is a good one for me to do asynchronously. I mean, I can send you guys a link and you can join if you'd want, but it'll be a lot of definitions. So I want to talk about vectors next time. A lot of you probably also know about them already, but it's going to be a lot of definitions. And so you probably don't need to be in class for that, technically speaking. But then next week, we'll pick up with this and using vectors describe some other cool things about 3 space that would really kind of set you up for the future. And hopefully so far it's been clear and it's been fun talking about this stuff, and a little bit of a refreshing experience from all the computational intensity of the first half of the semester. I think really talking about, just some ideas and seeing how concepts fit together is a really fun way to go about math. So hope you guys are enjoying that, and we'll kind of wrap up there. As I said, test 2 and the final online through Top Hat, you will receive information about that this weekend. Your test is next week. I'll try to get a practice test out to you guys as well to get used to the platform. And yeah, I think we'll end there. Are there any questions before we go? Any more questions, comments, concerns? Okay, all right, good. Yeah, we'll stop there. Enjoy the rest of your Friday. And oh yeah, I'll see you guys later. Head off to your next classes if you have them. And have fun, stay safe, stay healthy. We are going to stop there. So
Thank you.
Thank you.
thank you for joining, and I'll see you guys in the next one. So